Welcome to starry cosmos. Imagine a space utterly devoid of stars, galaxies, even the faintest glimmer of light. A region so immense that across it, countless billions of years would pass with no change. No new formations, no dying embers. It's a paradox, an emptiness that feels profoundly wrong within the grand design of all we observe. Scientists have begun to suspect the existence of these supervoids, colossal gaps in the fabric of space itself, stretching across hundreds of millions of light years. What forces could sculpt such unimaginable voids? And what do they whisper about the very origins of our universe? The initial conditions that birthed everything within them. Dim your lights, settle in, get comfortable, and let's begin. If these quiet journeys help you drift off, hit that like button and subscribe to Starry Cosmos so that the next journey through the vast expanse finds you when you need it. Okay, here's a 1,600-word narration for Supervoids, the darkest secrets of the cosmos, adhering to all the guidelines provided. Let us begin by considering the simplest assumption, the one that has held our minds captive since we first looked up at the night sky. We imagine that space, this vastness stretching out beyond anything imaginable, is fundamentally empty. A perfect vacuum, a silence unbroken except for the faintest whispers of radiation. But as you spend more time observing the cosmos through ever-increasingly powerful telescopes, and as our understanding of physics deepens, a fascinating challenge emerges, a persistent question about why space isn't completely empty. It's a puzzle that reveals hidden forces at play, shaping galaxies, guiding dark matter, and ultimately painting a portrait of a universe far more complex and surprising than we initially conceived. We begin by encountering something called cosmic voids, immense regions in the universe characterized by an extraordinarily low density of stars and galaxies. These aren't simply empty patches, they are colossal absences, spanning hundreds of millions or even billions of light years across. Imagine, if you will, looking out across a gigantic oceanic landscape, vast, seemingly featureless expanses, punctuated only by the occasional distant island. cosmic voids are similar, but instead of water and land, we're dealing with galaxies and the scant remnants of stars scattered sparsely throughout them. They are like colossal sinkholes in the fabric of space itself, where the concentration of matter is dramatically lower than average. The term void comes from a simple observation. When astronomers map the distribution of galaxies across immense scales, using surveys that count millions or even billions of distant objects, they consistently find these enormous gaps, these pockets of emptiness. The Hubble Ultra Deep Field, for instance, captured thousands of galaxies over a tiny patch of sky. And even within this constrained view, it revealed an abundance of these voids. Some of the largest known are roughly 1 billion light years across, distances that defy comprehension when you consider they represent the space between galaxy clusters, not areas filled with galaxies themselves. These voids aren't cold, lifeless places, though they're often populated by hot gas and magnetic fields, remnants from the early universe, gradually cooling as they spread out. They are, in their own way, dynamic environments, slowly changing over billions of years. But simply noting these cosmic voids isn't enough to explain them. It begs the question, why do they exist? What process could possibly create such enormous regions of emptiness within a universe that seems driven by gravity, a force that relentlessly pulls matter together? The answer lies in a fundamental component of our current cosmological model, and frankly, one of the most baffling aspects of it: dark matter. Dark matter isn't something you can see with telescopes. It doesn't interact with light in any measurable way. It doesn't emit, absorb, or reflect photons. We know it exists because of its gravitational effects on visible matter. Galaxies rotating faster than they should based solely on the amount of gas and stars within them. Clusters of galaxies behaving as if they contain far more mass than we can actually observe. And the way light bends around distant objects, an effect predicted by Einstein's theory of general relativity. Scientists suspect that dark matter makes up approximately 85% of all matter in the universe. This isn't a missing amount. It's a different type of matter altogether, with its own properties and behavior. Its existence was inferred decades ago from observations of galactic rotation curves, the speed at which stars orbit within galaxies. Without dark matter's gravitational pull, these outer stars would simply fly away from the centers of their respective galaxies. Now, let's consider how this invisible substance plays a crucial role in shaping large-scale structure formation. The early universe was remarkably uniform, a nearly homogeneous soup of particles and radiation. However, tiny fluctuations existed in the density of matter. Slight variations in temperature that acted as seeds for future structures. As the universe expanded and cooled, gravity began to amplify these initial density fluctuations. Denser regions pulled in more matter, becoming even denser, while less dense regions became even less dense, a process akin to water flowing downhill, gathering into depressions. This hierarchical growth is how galaxies, galaxy clusters, and the vast cosmic voids we've been discussing all came to be. But here's where the gravity of dark matter becomes particularly important, because it interacts with itself through gravity, but not with light. Dark matter started clumping together slightly earlier than ordinary matter. Baryonic matter, the stuff that makes up stars, planets, and us. These clumps of dark matter formed a kind of gravitational scaffolding, a framework upon which galaxies could then assemble. Ordinary matter, being affected by the electromagnetic force as well as gravity, was drawn into these pre-existing dark matter concentrations. It's like building a house. You need a strong foundation before you can erect walls and roof. The dark matter provided that initial foundation for galaxy formation. Early observations of void distribution, particularly those made using deep sky surveys like the Sloan Digital Sky Survey, SDSS, presented a puzzle. These surveys revealed that voids aren't randomly scattered throughout space. They tend to be arranged in a complex web-like structure. The largest voids are often located at the edges of this network, with smaller voids clustered together within larger structures. The distribution resembles a cosmic sponge, a dense central core surrounded by a network of interconnected gaps. This isn't just an aesthetic feature of the universe. It carries profound implications for understanding how gravity operates on large scales. The most compelling explanation for this observed void structure combines the influence of dark matter with the concept of cosmic inflation. Cosmic inflation, a theory developed to explain the homogeneity and isotropy, uniformity in all directions of the observable universe, hypothesizes that the very early universe underwent an incredibly rapid period of expansion. A tiny fluctuation blowing up to enormous size within fractions of a second. This inflationary epoch is thought to have stretched quantum fluctuations into the density variations we see today as seeds for structure formation. The prevailing model suggests that dark matter's gravitational influence played a key role in shaping these early density fluctuations, and as a result, the voids formed as areas where gravity couldn't overcome the initial amplified density fluctuations. In other words, regions of space with slightly lower gravitational potential, effectively less dense, were left behind, becoming the colossal cosmic voids we observe today. Furthermore, simulations based on this model accurately reproduce the observed distribution of voids and their interconnected web-like structure. However, it's important to acknowledge that our understanding is still incomplete. The nature of dark matter itself remains one of the biggest mysteries in modern cosmology. Is it composed of weakly interacting massive particles, WIMP, actions, sterile neutrinos, or perhaps something entirely beyond our current theoretical frameworks? The answer and answers are actively pursued through experiments searching for direct detection of dark matter, and by studying its gravitational effects with increasingly sensitive telescopes. As you contemplate the vastness of space and the existence of these incredible voids, remember that this is a universe still packed with surprises. The more we learn about it, the greater our appreciation for its complexity becomes, and the deeper our questions grow. The study of cosmic voids isn't merely about cataloging empty spaces. It's about uncovering the fundamental forces that govern the evolution of the cosmos and deciphering the secrets hidden within its deepest shadows. It's a reminder that even in seemingly desolate regions, the echoes of the early universe and the fingerprints of dark matter continue to shape our observable reality. I've aimed for the requested pacing, flowing prose style, and meticulous scientific grounding, while staying strictly within your specified parameters. Looking back now, it's almost impossible to fully grasp the sheer, breathtaking scale of what we've been able to witness. The universe doesn't simply exist. It has a history, a vast, unfolding narrative written across billions of years in light. And within that story, there are points where the expected patterns break down, revealing something profoundly unexpected. We find ourselves drawn to these anomalies, these deviations from the norm, and they offer a particularly compelling window into how our universe is truly constructed. Let's turn now to a cornerstone of this exploration, specifically a project born of patience, ingenuity, and an almost stubborn dedication to observation: the Hubble Deep Field. The Hubble Space Telescope has throughout its lifetime provided us with images that have fundamentally reshaped our understanding of the cosmos. But in 1995, a team led by astronomers like Andy Hudemeister set out on what seemed at the time a remarkably audacious undertaking to point the telescope at a single, seemingly unremarkable patch of sky for nearly 3 weeks. It's important to remember that Hubble was already an incredibly advanced instrument for its time. But even with its capabilities, they knew capturing a deep image like this would require immense effort and careful planning. And it did. The team had to painstakingly shield the telescope from sunlight and thermal noise, ensuring that every photon of light from distant galaxies would have a chance to register on the sensitive detectors. The result was released to the world in 1996, an image so profoundly detailed, so utterly filled with starlight. It felt as though you were peering directly into the heart of creation, a mere postage stamp-sized area of sky, smaller than our own Milky Way galaxy, contained over 10,000 galaxies, galaxies of every shape and size, from tiny dwarf ellipticals to enormous spiral giants, all huddled together in a breathtaking mosaic of light. It was as if someone had taken an impossibly small piece of the universe and displayed it for us to examine with exquisite clarity. The initial reaction amongst astronomers wasn't exactly one of immediate comprehension. The models we used to predict how galaxies should form and spread throughout space, the simulations based on our understanding of gravity, dark matter, and cosmic expansion, simply couldn't account for the density observed in this single field. These models, which had successfully predicted many aspects of galaxy formation over the years, suggested that galaxies ought to cluster relatively evenly across the sky, like a scattering of seeds dispersed by the wind. The distribution we were seeing, however, the sheer number of galaxies concentrated within these enormous voids, seemed utterly baffling. As you might imagine, this created quite a stir, and it fueled considerable debate within the astronomical community. It felt as if the universe was actively avoiding us, displaying a level of complexity that defied our established theories. What we were observing, in its simplest terms, pointed toward the existence of enormous gaps, vast voids in the cosmic web. These weren't simply empty spaces. They are regions where the distribution of galaxies is dramatically lower than what would be expected based on the overall density of matter in the universe. And what's even more surprising is that these voids aren't isolated bubbles. They are interconnected, forming a vast, three-dimensional network, the cosmic web, akin to the branches of a gigantic tree. The Hubble Deep Field observations were then followed up by subsequent deep field surveys. The ultra-deep field by the James Webb Space Telescope, for example, which has taken this concept even further, revealing galaxies that are significantly more distant and faint than previously imagined. Yet the core observation from 1995 continued to provide crucial context. It wasn't just the number of galaxies, it was where they were located, concentrated within these immense voids. We began to realize that these voids weren't just empty spaces. They seemed to be acting as gravitational anchors, attracting and holding galaxy clusters together. It's a concept known as the void galaxy correlation. The detail of the void galaxy correlation is quite remarkable when you consider how it was initially uncovered. Astronomers began noticing that galaxies within these voids tended to be smaller, less massive, and often more irregular in shape than galaxies found in denser regions of the universe. You see, gravity plays a significant role here, acting like an invisible hand, shaping the distribution of matter. The concentration of galaxies inside the voids has been linked to subtle gravitational influences, a kind of cosmic pull that effectively traps smaller galaxies within these massive empty spaces. It's not as if these voids prevent galaxy formation. Rather, they seem to direct it, guiding the growth of galaxies towards the densest regions of the network. The prevailing theory suggests that during the early universe, a process known as cosmic inflation, a period of incredibly rapid expansion, created immense fluctuations in the density of matter. These fluctuations seeded the structures we see today: galaxies, galaxy clusters, and yes, these vast empty voids. It's thought that regions containing lower densities were left behind after the inflationary epoch, resulting in these colossal gaps in the cosmic web. This doesn't mean inflation created everything, but it did set up the initial conditions for structure formation, creating certain areas of significantly lower density. However, the exact mechanism driving galaxy distribution within these voids remains an active area of research. Scientists suspect that dark matter, an invisible substance that interacts with gravity but not light, plays a crucial role in shaping the cosmic web and influencing the movement of galaxies within the voids. Dark matter is thought to form the scaffolding upon which visible matter, galaxies, stars, gas builds. The distribution of dark matter dictates the overall structure of the cosmic web, creating pathways for galaxies to flow along. Furthermore, recent simulations are suggesting a more dynamic role for void formation, that they are not just passive remnants of inflation, but actively formed through mergers between smaller voids and galaxy clusters over billions of years. These mergers would create even larger voids, further reshaping the overall cosmic web. It's an ongoing process of growth and decay, a constant dance of gravity influencing the distribution of galaxies throughout the universe. The Hubble Deep Field wasn't just a pretty picture. It was a catalyst for a fundamental shift in our understanding of cosmology. It demonstrated that the universe isn't simply a smooth, homogeneous expanse. It's a complex, interconnected network of structures, punctuated by these colossal, empty spaces. It reminded us that even our most sophisticated models can be challenged by observation, and that sometimes the greatest discoveries come from looking at seemingly unremarkable patches of sky. And as we continue to peer deeper into the cosmos with instruments like the James Webb Space Telescope, we can expect to uncover even more surprising secrets hidden within these vast voids, secrets that may ultimately reshape our understanding of how the universe came to be and what its ultimate fate may hold. The scale of this initial discovery, the sheer number of galaxies packed into such a small area, should give you pause. It's a potent reminder of just how much there is left to learn, how little we truly comprehend about the vastness that surrounds us. It invites you to consider not just the beautiful images, but also the profound questions they raise. The light from distant galaxies stretches across unimaginable distances, a testament to the sheer scale of the universe. But sometimes that light doesn't reach us at all. It's swallowed by darkness, a profound, unsettling darkness that has captivated astronomers for decades now. We speak of supervoids, immense regions of space where galaxies are shockingly sparse, and the distribution of matter is profoundly different than anywhere else we observe in the cosmos. And today, we'll be exploring how one of our most powerful tools, the Sloan Digital Sky Survey, is helping us to truly map these dark secrets, charting the contours of this bizarre landscape. The Sloan Digital Sky Survey, or SDSS for short, isn't simply a telescope. It's an enormous undertaking, a collaborative effort involving teams around the globe, and countless hours of data collection and analysis. It began in the early 2000s and continues to deliver an ever-increasing stream of information about our universe. Imagine, if you will, not just looking at the night sky through a single lens, but casting an eye across nearly all of it, almost every square degree of the heavens. That's essentially what the SDSS has done, using its massive telescopes located in New Mexico to capture images of hundreds of millions of galaxies, along with detailed measurements of their position, brightness, and spectrum. The light they emit broken down into its constituent colors. These spectra are incredibly important because they tell us how fast a galaxy is moving relative to us and what elements it's made of. The project was built around two primary instruments: the Sloan Legacy Survey Camera, SLACS, and the Sloan Spectroscopic Telescope, SST. SLACS produced those breathtakingly detailed images, hundreds of millions of them, really, that you often see when discussing the SDSS. But it was SST's spectroscopic capabilities that truly set it apart. By analyzing the light from these galaxies through their spectra, astronomers could determine not just how far away they were, but also what types of stars and gas were present within them, giving a much richer understanding of their composition and history. The raw data itself is publicly available, almost entirely free to use. A remarkable commitment that has fueled countless scientific discoveries beyond simply mapping supervoids. Now, let's talk about the scale of what the SDSS has achieved. As of today, this survey has mapped over 350 million galaxies, spanning an area of approximately 20 times the size of the full moon, and reaching a distance of roughly 8 billion light years. That's like trying to map every grain of sand on all the beaches on Earth. Only you're doing it with galaxies. What makes this data so valuable for our investigation into supervoids is its sheer density. Every single galaxy, every tiny point of light was precisely measured and recorded. This provides an incredibly detailed census of the universe's population, a baseline against which to compare these vast, empty regions. So, how many supervoids have scientists identified using SDSS best data? The answer is a staggering number. Over 300 distinct voids have now been mapped with astonishing precision. These aren't just small pockets of emptiness. They can be hundreds or even thousands of megaparsecs across. A megaparsec being roughly 3.26 million light years. To put that in perspective, the Milky Way galaxy itself is only about 100,000 light years wide, and the largest voids identified so far, like the Boötes Void and the Shapley Supervoid, are over 150 megaparsecs across. To visualize this, imagine a region of space larger than our entire observable universe. And that's roughly how enormous these voids truly are. But it's not just about their size. The distribution itself is incredibly puzzling. Scientists suspect that these supervoids formed early in the history of the universe, perhaps as little denser regions that then gravitationally dominated large swaths of space, pulling in dark matter and effectively cannibalizing nearby galaxies. It's a complex process involving the interplay between gravity, dark matter, which makes up approximately 85% of all matter, and the expansion of the universe itself. The prevailing theory suggests they were created during a period of accelerated expansion called inflation, which caused a rapid stretching of space shortly after the Big Bang. These initial density fluctuations then grew over billions of years, eventually leading to these enormous voids we're now observing today. It's important to understand that SDSS isn't just passively recording, it's actively shaping our understanding. To find these voids, astronomers use a technique called void detection. It begins with the raw images from SLACs and then applies sophisticated algorithms that identify regions of space where the density of galaxies is significantly lower than expected. A statistical anomaly that stands out against the background of the cosmic web. They also look for walls, which are filaments of galaxies connected to these voids, forming a network that permeates the universe. These walls represent areas where matter is concentrated and gravity is actively pulling things together. The survey's data isn't just used on its own. it's constantly being combined with other cosmological datasets, like measurements from the Planck satellite, which mapped the cosmic microwave background radiation to refine our models of how the universe evolved. This multi-pronged approach helps to build a more complete and robust picture of, well, everything really. The SDSS, in effect, is providing a meticulous map that allows theorists and observers alike to test their hypotheses about the fundamental nature of space and time. Furthermore, because the data is so vast and accessible, citizen scientists, amateur astronomers who contribute their time and expertise play a significant role in the ongoing analysis. They sift through the images, identifying galaxies and verifying the results produced by automated algorithms, essentially extending the reach of the survey's capabilities exponentially. It's an extraordinary example of collaboration between professional researchers and passionate volunteers. Now, studying supervoids isn't just about counting them. It's about understanding why they exist. Are they truly random occurrences in a largely uniform universe? Or are there subtle clues hidden within the distribution that reveal something deeper about the underlying physics, perhaps hinting at new particles or forces we don't yet fully comprehend? The challenges are significant, and as you might expect, there is still considerable debate among cosmologists regarding their origin. One fascinating finding emerging from SDSS data is a correlation between the size of supervoids and the density of dark matter within them. The larger the void, the more dense the surrounding dark matter appears to be. A counterintuitive relationship that continues to puzzle scientists. Some theories suggest that these voids are not simply empty spaces, but rather regions where dark matter has been stripped away, leaving behind a relatively sparse distribution of galaxies. It's like peeling back layers of an onion, each layer revealing more complex and unexpected details about the composition of our universe. As we continue to analyze this colossal dataset produced by the Sloan Digital Sky Survey, it becomes clear that these supervoids are far more than just large, empty spaces. They represent a fundamental challenge to our current understanding of cosmology, a stark reminder of how little we truly know about the nature of dark matter and the forces that govern the evolution of the cosmos. The data from SDSS is not simply filling in gaps on a map. It's forcing us to rewrite sections of the narrative, looking at the sheer scale of the voids, considering their distances, billions of light years. You begin to understand how isolated these regions are and how effectively they shield themselves from the influence of the rest of the universe. It prompts a certain reflection about our own place within this grand scheme. Just one tiny corner of an overwhelmingly large and mysterious cosmos. And it invites you again to consider not just the beautiful images and meticulously collected data, but also the profound questions they raise. What are these voids really telling us about the nature of dark matter? What processes led to their formation? And ultimately, how do they fit into our broader understanding of the universe's past, present, and future? The exploration continues, driven by the remarkable insights afforded by the Sloan Digital Sky Survey, a testament to human curiosity and our relentless desire to unravel the secrets of the dark. The exploration continues, driven by the remarkable insights afforded by the Sloan Digital Sky Survey, a testament to human curiosity and our relentless desire to unravel the secrets of the dark. And as we peer deeper into the vastness, seeking to understand what lies beyond observation, we encounter phenomena that whisper intricate tales about the very fabric of the cosmos, stories revealed not through blazing light, but through subtle distortions in the faint echo of the Big Bang itself. Today, we turn our attention to one such phenomenon, the Sunny-Eve-Zeldovich effect. It's a delicate dance between photons and dark matter, a trick of the light that offers us an invaluable window into the shadowy realm where most of the universe resides. Let's begin with the cosmic microwave background, or CMB, that faint afterglow of creation, a uniform bath of microwave radiation bathing all of space. Imagine it as the residual warmth from the very first moments when the universe cooled enough for atoms to form. effectively stopping the continuous scattering of photons and allowing them to propagate freely. It's remarkably consistent across the sky, a testament to the homogeneity of the early universe. However, this apparent uniformity is not absolute. Tiny fluctuations, temperature variations on a scale incredibly small, yet encompassing the entire observable universe, imprinted themselves upon that primordial glow. These fluctuations are seeds for all the structure we see today. Galaxies clustering together, forming vast cosmic webs and concentrating in enormous voids. And it's within these voids, these huge absences of matter, that the Sunyaev-Zeldovich effect comes into play. The effect itself is a consequence of interaction between photons from the CMB and free electrons. Electrons not bound to atoms, but jostling freely through space. Now, as those CMB photons travel across the universe, some inevitably encounter these free electrons. And here's where things get interesting. When a photon interacts with an electron, it doesn't just bounce off. It can actually scatter off of it. This scattering is entirely dependent on the energy of the photon. If the photon has relatively low energy, this is crucial. Its wavelength will be slightly stretched as it interacts with the electron. Conversely, if the photon has higher energy, its wavelength will be compressed. This change in wavelength, this shift towards longer wavelengths, is what we call the Sunyaev-Zeldovich effect. Now, consider a CMB photon traveling through a void, an area of extremely low matter density. Because the density is so low, there are far fewer free electrons to scatter off of the CMB photons. Consequently, many of those interacting photons will experience this stretching, this redshift, as they traverse the void. As you follow the path of millions of these individual photons, you'll notice a distinct pattern, a slight brightening in the direction of increasing redshift, as if the void itself were somehow amplifying the signal. It's not that the CMB is actually becoming brighter. Rather, the observed brightness, the amount of radiation we detect, increases because it becomes more stretched. And this stretching precisely correlates with the density of dark matter within the void. The effect is named after astrophysicists Yuri L. Sunyaev and Alexander S. Zeldovich, who independently predicted its existence in 1965. A remarkable feat of theoretical physics based on Einstein's theory of general relativity and the scattering of photons. Their work was initially met with skepticism, largely because the effect is incredibly subtle, often just a few parts per million, and difficult to distinguish from instrumental noise. However, as observational capabilities improved and more sensitive instruments came online, like the Wilkinson Microwave Anisotropy Probe, WMAP, and, most recently, the Planck satellite, it became increasingly clear that the Sunyaev-Zeldovich effect isn't just a prediction. It's a real phenomenon, and a remarkably powerful one. But how precisely does this redshift provide information about dark matter? Well, dark matter, the mysterious substance comprising approximately 85% of the total mass in the universe, doesn't interact with light in any significant way. It doesn't absorb, reflect, or emit photons. Therefore, it doesn't directly contribute to the CMB spectrum itself. However, it does gravitationally influence the distribution of ordinary matter, the hydrogen and helium that makes up stars, galaxies, and planets. Dark matter forms a kind of scaffolding, holding these structures together. This gravitational field, in turn, subtly affects the free electrons within voids, causing them to bunch up, creating regions with higher electron density. And as we've established, it is this heightened electron density that leads to a greater number of CMB photons being scattered and redshifted when traversing those voids. Think about it like this. Imagine placing a heavy ball on a trampoline, creating a dip in the surface. Ordinary matter, galaxies, for example, would similarly create gravitational distortions in the distribution of dark matter within a void. These distortions would then influence the density and behavior of the electrons, leading to variations in the Sunyaev-Zeldovich signal. The magnitude of these variations directly relates to the strength and extent of the underlying dark matter distribution. This is why the Sunyaev-Zeldovich effect as a probe of void density, a way to map out the distribution of dark matter in the universe without actually seeing it directly. Scientists use observations of this subtle brightening, carefully analyzing the CMB temperature fluctuations, to construct detailed maps of these voids, revealing their shapes, sizes, and relative densities. These maps are then compared with simulations of how dark matter would have evolved over cosmic time, allowing researchers to test our theoretical models and refine our understanding of its nature. Importantly, the Sunyaev-Zeldovich effect isn't just about mapping voids. It also provides a way to measure the growth of structure in the universe. As the universe expands, dark matter clusters together under its own gravity, forming larger and larger structures. The Sunyaev-Zeldovich signal from these growing structures, galaxies and galaxy clusters, changes over time as they interact with the CMB photons and the free electrons along their paths. By carefully studying these changes, astronomers can constrain the parameters of cosmological models. Things like the density of dark matter itself, the rate at which the universe expands, and the nature of dark energy, providing crucial evidence for our understanding of the cosmos's evolution. Furthermore, the effect isn't limited to simply observing voids. It can also be used to study clusters of galaxies. As a galaxy cluster collapses under gravity, the hot gas within its boundaries interacts with CMB photons, producing a Sunyaev-Zeldovich signal that is significantly stronger than what we observe in empty voids. By analyzing this amplified signal, astronomers gain insights into the dynamics of the cluster's evolution and the distribution of matter within it. The research continues to evolve, driven by increasingly sophisticated telescopes and analytical techniques. Current and future missions, such as the Roman Space Telescope, which will utilize a coronagraph to block out starlight, are poised to provide even more precise measurements of the Sunyaev-Zeldovich effect, pushing our understanding of dark matter distribution to new levels of detail. It's a testament to the ingenuity of physicists and astronomers that such a subtle distortion in the cosmic microwave background can offer such profound insights into the fundamental constituents and dynamics of the universe. As we zoom out from these individual voids, considering their place within the grand tapestry of the cosmos, it's truly humbling. The Sunny-Zeldovich effect is but one thread in a vastly complex pattern, a silent language spoken by the light itself, revealing the secrets hidden within the darkness. And as we continue to listen more closely, refining our instruments and deepening our theoretical frameworks, we are certain to uncover ever more astonishing revelations about the cosmic dance of matter, energy, and space-time. The quest to understand the nature of dark matter, driven in part by this remarkable effect, remains one of the most compelling endeavors in modern astrophysics, a journey into the heart of what makes the universe the universe. The faint echo of that previous question, the nature of dark matter, driven in part by this remarkable effect, lingers softly as we turn our attention to a far more immediate influence upon the grand tapestry of space. We move from seeking answers about invisible substance to understanding forces actively shaping the movement and arrangement of galaxies, focusing now on something vast and profoundly mysterious, the Great Attractor. It's not a place you can point to with a telescope. It doesn't appear as a bright star or a swirling nebula. Instead, it is an unseen mass, a gravitational anomaly that exerts a powerful pull, a silent anchor within our local region of the universe. Imagine for a moment standing on a vast ocean, feeling the subtle tug of currents even when you can't see them directly. The Great Attractor presents itself in a similar way. Its effects are evident through the movements of galaxies, like ripples spreading outwards from a stone dropped into that water. It was initially detected in the late 1990 by studying the peculiar motions of radio galaxies, distant beacons whose light has traveled for billions of years to reach us. These galaxies weren't simply drifting randomly. They were exhibiting a systematic flow, a collective drift towards a point in space that astronomers couldn't directly observe. The evidence was compelling. These galaxies, spread across hundreds of millions of light years, were all being drawn together with a force far exceeding what could be accounted for by the visible matter within our own local group. The cluster of galaxies, including the Milky Way and Andromeda. This led to the realization that something massive, something substantial, lay hidden just beyond our immediate field of view, exerting its gravitational dominance. Scientists estimate that the Great Attractor contains a mass roughly 3 times greater than that of the entire local group, a truly astronomical amount of matter packed into an area, perhaps only a few hundred light years across. It is primarily composed of dark matter, reinforcing the idea that much of the universe's substance remains shrouded in mystery to us. But what is this unseen mass? The leading theory. And it's important to note that this is still a hypothesis vigorously tested by researchers, points toward a collection of massive elliptical galaxies and galaxy clusters concentrated into a single point, a gravitational well pulling everything nearby inward. These galaxies themselves are remnants of ancient cosmic collisions and mergers, drawn together over billions of years by the relentless dance of gravity. Recent observations using the Gaia spacecraft, a marvel of modern astronomy that meticulously charts the positions and motions of over 1 billion stars in our Milky Way, have illuminated this structure with unprecedented detail, revealing a network of galaxies and filaments extending far beyond what was previously known, converging towards the Great Attractor. The effects of its pull are not limited to just influencing the movements of distant radio galaxies. It also plays a key role in shaping the distribution of galaxies within the vast voids, those enormous, nearly empty spaces between galaxy clusters that dominate much of the observable universe. You see, these voids aren't simply empty. They are influenced by the gravity of surrounding structures, and the Great Attractor is a significant contributor to this gravitational landscape. Massive objects like the Great Attractor act as anchors, drawing in nearby galaxies and influencing how those galaxies then populate the space around them. It's not a simple one-way pull, though. The voids themselves are shaped by the distribution of matter throughout the cosmos. creating feedback loops where gravity influences both void formation and galaxy clustering. The very patterns we observe in the large-scale structure of the universe, the cosmic web of filaments and voids, are profoundly affected by this hidden gravitational force. Let's visualize what that looks like. Imagine a vast sponge riddled with holes. The sponge represents our observable universe, while the dark matter, including the great attractor, forms the dense material within it. Now, as you squeeze the sponge, you can see how it distorts and compresses the areas around the pressure points, creating a network of connected cavities. That's essentially what's happening on an immense scale in our local universe. Galaxies are being drawn towards the great attractor, creating concentrations of matter and influencing long-range flows. Researchers have used sophisticated computer simulations to model this gravitational interaction. These simulations take into account the distribution of dark matter, the motions of individual galaxies, and the complex web of gravity within our region of space. A task requiring immense computing power and careful refinement. The results consistently show that the great attractor is indeed responsible for the observed peculiar velocities of galaxies across vast distances. It's a testament to how gravity operates on scales far beyond our everyday experience, a force capable of shaping entire cosmic landscapes over billions of years. The visualizations you'll see now present a representation of this gravitational field, built from data gathered by missions like Gaia and the Hubble Space Telescope. Represented here are the velocities of hundreds of thousands of galaxies, overlaid onto a map of our local universe, a kind of gravity flow chart, if you will. Notice how the arrows point towards a central region, the location of the great attractor. These aren't just random fluctuations. The line of sight to each galaxy has been carefully calculated to reveal its true velocity, independent of the motion of the Milky Way itself. Any galaxies appearing to drift toward this unseen mass are being actively pulled in by it. The color coding indicates the magnitude of that pull. Darker colors represent stronger gravitational fields, it's crucial to understand that we are still learning about the great attractor and its influence, its exact composition, the precise distribution of dark matter within it, and the subtle interactions with other gravitational sources in our local region remain subjects of ongoing research. Furthermore, models continue to be refined as new data emerges from telescopes like Hubble and James Webb, providing an ever more detailed picture of this hidden behemoth. The study of the great attractor is intimately connected to our broader understanding of dark matter and its role in shaping the universe. Dark matter's gravitational influence isn't confined to creating voids. It's a fundamental component of galaxy formation, acting as a scaffolding around which visible galaxies assemble. Without dark matter's unseen hand guiding the motions of galaxies, structures would likely be too dispersed. The universe wouldn't have evolved into the complex web of clusters and voids we observe today. The great attractor serves as a particularly compelling demonstration of this principle, a localized region where both dark matter and visible galaxies are profoundly affected by an enormous gravitational anomaly. As you gaze upon these visualizations, consider the immense distances involved, billions of light years across. The effects felt here in our relatively small corner of space are staggering, demonstrating the sheer scale and power of gravity operating on cosmic scales. And remember that we're not simply observing a random collection of galaxies. We're witnessing a carefully orchestrated dance, guided by forces still largely beyond our complete comprehension. The ongoing investigation into the great attractor and similar gravitational mysteries throughout the cosmos continues to push the boundaries of astrophysical knowledge, challenging us to refine our theories and explore the fundamental nature of space, time, and the very fabric of reality. It's a reminder that even in an age of increasingly powerful telescopes and sophisticated simulations, the universe still holds countless secrets waiting to be unearthed through patient observation, rigorous analysis, and a deep-seated curiosity about the cosmos around us. The quest to understand this localized gravitational anchor will undoubtedly illuminate broader questions about dark matter distribution, galaxy evolution, and the overall structure of our expanding universe for decades to come. Now, as we've considered the relative quietude of our own local group, the cluster of galaxies that includes the Milky Way and Andromeda, we naturally turn our gaze outward, seeking to understand what lies beyond. It's a question both profoundly simple and incredibly complex, one that has occupied astronomers for decades now. We begin to realize that this seemingly isolated patch of space is merely a small island in an ocean far larger than we could have initially imagined. An ocean punctuated by vast, echoing silences, the supervoids. And as we push our mapping efforts ever further outward, toward the edges of what we can observe, a remarkable pattern begins to emerge. These enormous voids, these seemingly empty spaces of space, remain stubbornly consistent in their properties across immense distances. That is, they aren't random aberrations, but rather part of an underlying geometry. It's a suggestion that points to something fundamental about the very fabric of the universe itself. Consider for a moment what we expect if the cosmos were truly random. If galaxies and clusters of galaxies simply formed independently, scattered throughout space without any particular order, then we would anticipate seeing voids of all shapes, sizes, and densities at every conceivable distance. We'd expect to find colossal gulfs next to dense walls, isolated pockets amidst swirling groups, a chaotic jumble reflecting no underlying structure. But the data tells us something quite different. When we map the distribution of galaxies across billions of light years of space, using surveys like the Sloan Digital Sky Survey and more recent deep field images from telescopes like Hubble and James Webb, we find that the largest voids remain remarkably similar in size and density, regardless of how far away they are. The statistics hold 100 million cubic light years across, for instance, seems to be a statistically preferred scale for these immense absences. And it's not simply a matter of occasional coincidence. It is observed repeatedly, spanning regions that cover tens of hundreds of millions of years of cosmic evolution and extraordinary consistency, suggesting the scales we are seeing are deeply connected. This uniformity isn't easily explained by simple chance. The universe, as we understand it, the lambdictum model, describes a cosmos dominated by dark energy, driving accelerated expansion, and substantial amounts of dark matter exerting gravitational influence. Yet, even with these key components in hand, the observed consistency of supervoids presents a challenge to our current understanding. We can build models that incorporate variations in dark matter density, accounting for initial fluctuations during the Big Bang, but reproducing this precisely consistent void distribution across scales so vast requires invoking mechanisms far more complex than originally anticipated. It's as if the universe itself is subtly sculpting these voids into a particular form, a form dictated not by randomness, but perhaps by underlying physics we don't yet fully grasp. Let's look at some examples of these cosmic deserts. The Boötes Void, for instance, located approximately 330 million light years from Earth, a distance still staggering to contemplate, is one of the largest known voids in our observable universe. It spans roughly 320 million cubic megaparsecs, or about 140 million cubic light years, making it nearly 3 times as large as the sphere encompassing our own local group. Its existence was first suggested by a team led by Dr. James Gunn of Johns Hopkins University, who analyzed data from the Sloan Digital Sky Survey and saw a significant deficit of galaxies in that region. Later, surveys using the Dark Energy Survey captured its unmistakable emptiness with astonishing detail, revealing the lack of any discernible gravitational pull, a profound silence amidst the cosmic noise. Then there is the Great Void, located significantly farther away, at approximately 1.7 billion light years from Earth. It's a truly immense structure, roughly 250 million cubic megaparsecs in size, and is notable for its especially large scale. It dramatically illustrates how these voids continue to exist on scales far larger than even the Boötes Void. And there are countless others: the Shapley Supervoid, the Hercules Corona Borealis Supervoid, and many more recently identified through dedicated mapping projects. The implications of this uniformity extend beyond simply refining our cosmological models. It forces us to reconsider the nature of dark matter itself. The standard model suggests that dark matter constitutes roughly 85% of the total mass in the universe. It's an invisible substance that interacts gravitationally but does not emit or absorb light, making its presence detectable only through its gravitational effects. However, the precise distribution of dark matter, how it clumps together to form galaxies and clusters, and how it contributes to the formation of voids, is still a subject of intense debate. Perhaps supervoids are created by regions where dark matter is less abundant than expected, acting as gravitational sinks that prevent galaxy formation in those areas. Or perhaps they're sculpted by some previously unknown process, a kind of cosmic vacuum cleaner pulling out the dark matter, leaving behind these expansive silences. It's a puzzle with tremendous ramifications for our understanding of what dominates the cosmos. Furthermore, this consistency challenges the idea that the universe is expanding uniformly in all directions. While we observe Hubble's law that galaxies recede from us at speeds proportional to their distance, the prevalence of supervoids suggests that there might be localized regions where expansion is significantly slower than average. These voids could represent areas where the fabric of space-time itself is subtly warped, creating pockets of reduced expansion rate. Exploring these anomalies would require incredibly detailed observations and sophisticated simulations, pushing the boundaries of our current capabilities. The existence of these colossal voids isn't merely a curiosity. It provides a fundamental constraint on what cosmological models can achieve. If we want to accurately reproduce the observed distribution of supervoids, their size, density, and consistency, we need to invoke mechanisms that go beyond the standard lambdictum model. This suggests that our current understanding of dark matter, dark energy, and perhaps even gravity itself, is incomplete. It's a call for new ideas, new observations, and a willingness to challenge long-held assumptions about the structure and evolution of the universe. Scientists suspect that the answer may lie in exploring modifications to Einstein's theory of general relativity, potentially involving higher-order curvature terms or alternative theories of gravity. Others are investigating the possibility that the voids aren't empty at all, but rather filled with a previously unrecognized form of matter or energy. Or perhaps they represent bubbles within an eternally inflating multiverse, regions where inflation has ended, prematurely leaving behind these vast, echoing spaces. And as we continue to observe further and further into this cosmic ocean, using instruments like the James Webb Space Telescope and future generations of extremely large telescopes that will probe deeper than ever before, we can expect even more surprising discoveries. The universe is full of mysteries, of absences as well as presences, and it's in these quietest corners, within these seemingly empty voids, that we may ultimately find the most profound answers to the biggest questions about our existence. The uniformity itself, this persistent echo of emptiness at vast scales, suggests a deeper order, a hidden choreography in the grand dance of the cosmos. And as we unravel it piece by piece, we bring ourselves closer to understanding not just what is out there, but why. The question now isn't simply where these colossal voids reside, their emptiness stretching for hundreds of millions of light years, but why galaxies seem so persistently drawn to them, like moths to a distant, almost unnerving flame. The sheer scale of the void is difficult to truly comprehend. It's a region where the density of matter is dramatically lower than average, an absence within an already immense darkness. And yet, within this vacuum, we observe galaxies, billions of them, clustered together in formations that seem strangely deliberate, almost as if seeking refuge in the nothingness. This presents, then, a fundamental puzzle. How does anything form and persist within such profound emptiness? The prevailing theory, and one that has gained considerable traction, centers on gravitational instability, an inherent tendency for structures to grow within underdense regions of space. Imagine a vast sea where pockets of slightly higher density begin to coalesce, attracting surrounding matter through the gentle tug of gravity. These initial clumps then become seeds around which further material accumulates, eventually forming larger and larger structures, galaxies themselves, nestled within the relatively isolated expanse of the void. But this isn't a simple accumulation. It's a process heavily influenced by what we understand as dark matter. Dark matter, you see, doesn't interact with light, meaning we can't see it directly. However, its gravitational influence is readily apparent, shaping the distribution of visible matter throughout the universe. These voids, particularly, are thought to be permeated with enormous halos of dark matter, vast, invisible shells extending far beyond the boundaries of any discernible galaxies within. This dark matter halo effectively creates a local gravitational potential well, pulling in surrounding galaxies like tiny pebbles circling a larger stone. Now, simulations have become indispensable tools in exploring these intricate relationships. Cosmologists employ powerful supercomputers to model the evolution of the universe, starting from the very early moments after the Big Bang and running them forward, simulating everything from the formation of galaxies to the distribution of dark matter. These aren't simply visual representations. They are exquisitely detailed mathematical models that incorporate the known laws of physics, general relativity, quantum mechanics, thermodynamics, along with our current understanding of cosmology. Using these simulations, researchers can tweak various parameters: the density of dark matter, the strength of gravity, the rate of expansion, and observe how galaxies form and migrate within a given void environment. The results often reveal a striking correlation. Voids tend to be filled with galaxies that are significantly less massive than those found in denser regions of space. It's as if the vast emptiness somehow inhibits the growth of individual galaxies, leading them to cluster together into looser, albeit still substantial, groups. Scientists suspect this has something to do with the ability of dark matter halos to retain gas, the raw material for star formation over long periods. Dense environments, by contrast, tend to strip away gas through interactions between galaxies and their surrounding environment, effectively halting or severely limiting further star birth. So the void, paradoxically, might be a sanctuary for smaller galaxies that have weathered intense gravitational encounters elsewhere. However, even with these sophisticated simulations, a complete answer remains elusive. It's a remarkably complex puzzle with many moving pieces. One persistent challenge lies in accurately modeling the effects of dark matter. While we know its influence is significant, the precise nature of dark matter itself continues to be one of the biggest mysteries in modern physics. Is it made up of weakly interacting massive particles, WIMP actions, or something else entirely? The simulations depend heavily on assumptions about its properties, and variations in these assumptions can lead to dramatically different outcomes. Furthermore, the interplay between dark matter and baryonic matter, the ordinary matter that makes up stars, planets, and everything we observe directly, is incredibly subtle and difficult to capture fully in a simulation. The gravitational influence of dark matter doesn't simply pull galaxies in. It also warps space-time around them, affecting how light travels and influencing the distribution of gas within the galaxies themselves. As galaxies move through voids, they interact with this warped space-time, leading to complex, non-linear effects that are difficult to predict. Another competing theory suggests a role for void galaxy connection, a specific process by which galaxies in voids acquire their stellar content and structure. One prominent idea proposes that these voids aren't simply empty spaces. They may have been sites of intense early star formation, generating vast reservoirs of gas-rich dwarf galaxies. Smaller, fainter galaxies, often overlooked in broader surveys. As the universe expanded, these early galaxies would have drifted into the voids, gradually accumulating mass through gravitational capture and mergers. The older stars in these captured galaxies, then slowly decay over billions of years, creating the faint luminosity we observe today as a galaxy within a void. It's a slow, gradual process, one that requires a specific set of conditions to unfold, conditions that might have been more prevalent in the early universe. There's also speculation about gravitational sculpting, where the subtle pressure from dark matter halos subtly shapes the morphology of galaxies as they migrate through voids. The elongated shapes seen in some void cluster galaxies could be a consequence of this ongoing, low-level gravitational interaction, like a gentle shaping by an invisible force. Recent observations using the James Webb Space Telescope are offering tantalizing new insights into these dwarf galaxies within voids, revealing unexpected levels of star formation and providing clues about their origins and evolution. The telescope's ability to peer back in time through the redshifted light from distant galaxies is allowing astronomers to study these systems at a level of detail previously unimaginable. We're beginning to see that many of these void cluster galaxies harbor surprisingly large numbers of stars for their size, suggesting that they may have undergone periods of intense star formation activity, perhaps fueled by mergers with smaller companions or triggered by encounters with tidal forces. And as we continue to study the distribution of galaxies across vast cosmic scales, utilizing the data from telescopes like Hubble and surveys like DESI Dark Energy Survey, patterns are emerging that further complicate the picture. The statistical properties of void galaxy clusters, their morphology, their stellar populations, their distances, don't perfectly align with any single theoretical model. The truth is, we're only beginning to scratch the surface of this extraordinarily complex phenomenon. It's likely that a combination of factors, gravitational instability, dark matter halos, early star formation, and subtle gravitational interactions all play a role in shaping the distribution of galaxies within these colossal voids. Perhaps the most compelling aspect isn't finding one definitive explanation, but understanding the diverse mechanisms at work, appreciating the intricate web of processes that connect the void to its stellar inhabitants. The universe continues to hold its secrets close, and while we relentlessly pursue knowledge through observation, simulation, and theoretical modeling, it remains a humbling reminder of how much we still have to learn about this immensity. The very act of seeking answers within these dark, empty regions illuminates our understanding of the fundamental forces that govern the cosmos, prompting even more profound questions about our place in its grand design. Determining answers within these dark, empty regions illuminates our understanding of the fundamental forces that govern the cosmos, prompting even more profound questions about our place in its grand design. Now, let's turn our attention to a rather unsettling aspect of this cosmic landscape: measuring the size of supervoids. It's a task far more complex than simply looking out into the darkness and guessing at how big it is. We are essentially trying to map the absence of things, an endeavor that immediately reveals its own challenges. The very nature of these vast, empty spaces makes accurate measurement exceptionally difficult, requiring sophisticated observational techniques and careful consideration of potential biases. Our primary methods for estimating supervoid sizes rely fundamentally on the distribution of galaxies. Astronomers look at incredibly deep fields of space, snapshots capturing millions of galaxies across billions of light years, seeking patterns in how these galaxies are clustered together. The prevalent assumption is that galaxies tend to group around large structures, forming filaments and sheets that crisscross the universe like a cosmic web. Supervoids, by contrast, appear as immense gaps within this structure, regions where galaxy density is significantly lower than average. One technique, often called galaxy counting, involves meticulously cataloging the number of galaxies residing within a specific volume of space. The larger the area with fewer galaxies detected, the larger the void we suspect. It's like trying to gauge the emptiness of a room by simply counting how many objects are missing. A surprisingly tricky endeavor when those missing objects are spread across vast distances. Furthermore, statistical analysis is applied to these galaxy counts, looking at how likely it is that such an empty region would appear purely by chance. To bolster confidence in the detection of a genuine supervoid. However, this method isn't without its significant pitfalls. The density of galaxies isn't perfectly uniform throughout the universe. There are fluctuations, and those fluctuations can mimic the appearance of a void. Dwarfs galaxies, small, faint galaxies, often missed by surveys, can obscure the true extent of a supervoid. They are like tiny pebbles scattered across a very large plane, creating an illusion of emptiness where it doesn't truly exist. Dust within our own Milky Way galaxy also creates this effect on local scales, making it difficult to accurately assess the distribution of distant galaxies. Moreover, projection effects can distort our perception because we observe the universe along its line of sight. A 3D surface projected onto a 2D image. Distances can appear compressed or stretched, influencing how we interpret galaxy counts and potentially leading us to overestimate or underestimate void sizes. Another powerful technique astronomers employ is weak gravitational lensing. This method leverages Einstein's theory of general relativity, which predicts that massive objects warp the fabric of space-time around them. As light from distant galaxies passes near a large mass, like a supervoid, its path bends slightly, a phenomenon known as gravitational lensing. This subtly alters the appearance of the background galaxy. We see it stretched or distorted. By meticulously analyzing these distortions across many galaxies in a particular region and measuring the statistical pattern of the distortion, scientists can infer the total mass present within that region. Because supervoids are essentially regions of low mass density, the degree of lensing, the amount of stretching observed, can provide a remarkably precise measurement of their size. It's like feeling for an invisible hand. By noticing how objects nearby seem to be subtly pulled in its direction. This method is particularly useful because it doesn't rely on directly counting galaxies. Instead, it detects the presence of mass through its gravitational effects. Despite these sophisticated methods, measuring supervoid sizes remains a daunting challenge. The sheer scale of these regions, often spanning hundreds or even thousands of megaparsecs. A megaparsec is roughly 3.5 million light years, means that any measurement inherently contains significant uncertainty. Each galaxy we count, each distortion we detect, contributes a small piece of the puzzle. But piecing together this scattered information to determine the precise boundaries of a supervoid requires enormous computational power and meticulous statistical analysis. Furthermore, our knowledge of the overall distribution of matter in the universe, something we still refine with each new observation, introduces further uncertainties into any size estimation. We are essentially trying to reconstruct a gigantic puzzle with many missing pieces and some distorted edges. Current estimates place the largest known supervoids at around 300 megaparsecs across, an area larger than our own Milky Way galaxy and its immediate stellar neighbors. The Boötes Void, located in the direction of the constellation Boötes, is currently considered one of the most prominent examples, identified through both galaxy counting and weak gravitational lensing studies. The Shapley supervoid, a similarly immense region situated between the constellations Perseus and Andromeda, also stands as a leading candidate for the largest known void, boasting an estimated diameter exceeding 250 megaparsecs. However, it's important to emphasize that these figures are constantly being refined as new data become available from increasingly sensitive telescopes like the James Webb Space Telescope, JWST, and the Vera C. Rubin Observatory, LSST. These future instruments promise to dramatically improve our ability to detect faint gravitational lensing signals and catalog galaxies with unprecedented precision, potentially unveiling even larger and more distant supervoids that we have yet to discover. The ongoing effort to map these colossal voids also has broader implications for understanding the evolution of the universe. The distribution of matter in the cosmos is not perfectly uniform. It's sculpted by gravity into a network of filaments sheets and bubbles, the cosmic web. Supervoids are thought to have formed through the collapse of density fluctuations in the early universe, regions where dark matter gravitationally attracted surrounding material, eventually repelling it and creating these immense empty spaces. The existence of supervoids provides crucial evidence for the theory of dark matter, as its gravitational pull is necessary to explain their formation and stability. Examining the size distribution of supervoids, how they are clustered together and separated, can also offer insights into the large-scale structure formation process and the fundamental physics governing the expansion of the universe. Consider this: the vastness of these voids poses a fundamental question about the fate of our own galaxy and the Milky Way's place in the grand scheme of things. Our region within the cosmic web is relatively dense, surrounded by galaxies and filaments. We are tucked into a relatively stable environment compared to those adrift within the supervoids, regions that appear to be almost entirely devoid of galaxies. It raises questions about why certain regions of the universe become so exceptionally empty, and whether these voids represent a fundamental limit on how matter can coalesce over cosmological timescales. Furthermore, subtle variations in the distribution of dark matter, which permeates throughout space but doesn't interact with light, may ultimately hold the key to unlocking the mysteries surrounding supervoids. Scientists are developing increasingly sophisticated simulations that incorporate detailed models of dark matter interactions to better understand how these voids formed and evolved. These simulations attempt to recreate the conditions of the early universe, allowing researchers to test different theoretical scenarios and assess their plausibility. The inherent complexity of modeling such vast scales, incorporating billions of particles interacting over hundreds of millions of years, presents a significant computational hurdle, demanding immense computing power and innovative algorithmic techniques. Despite the challenges, astronomers continue to relentlessly pursue answers through observations and increasingly powerful simulations. Each new measurement of a supervoid's size, each refined understanding of its formation mechanism brings us incrementally closer to grasping the profound implications of these enigmatic cosmic voids. As we push the boundaries of our observational capabilities and theoretical models, we are not only expanding our knowledge of the universe's structure, but also questioning our own place within it. A humbling exercise that underscores the truly immense scale and ongoing mysteries of this extraordinary cosmos. The persistent effort to map and comprehend these dark, empty regions illuminates not just the distribution of galaxies, but the very processes shaping the fate of the universe itself, prompting even more profound questions about our place in its grand design. Now settle in, get yourself comfortable, and let's begin. The vastness we've explored, the swirling galaxies, the distant quasars, they've revealed a universe teeming with activity, an intricate dance of gravitational forces and energetic phenomena. Yet within that grand choreography, there exist spaces utterly devoid of it. The supervoids, these colossal regions of emptiness, aren't simply gaps in space. They are, arguably, the most extreme environments we can find in this cosmos, offering a unique laboratory for probing the deepest mysteries of dark matter and its influence on the structure of the universe. Consider the sheer scale of these voids, some stretching hundreds of millions of light years across, encompassing regions larger than our own Milky Way galaxy. The implications of such immensity are staggering when you contemplate that within this emptiness, there's practically nothing to impede the flow of gravity itself. The concept of supervoids first emerged in the late 1980, driven by observations of the angular correlation function of galaxies. This function describes how frequently galaxies cluster together across vast distances. Statistical analyses revealed a surprising anomaly. Galaxies weren't clustered as uniformly as predicted by simulations based solely on visible matter. The stars and gas we can directly observe. The simplest explanation was that there were enormous, nearly empty regions, the supervoids, existing between these galaxy clusters, essentially creating a sea of space with relatively few galaxies. It's important to note, however, that these voids aren't uniformly empty. They contain a surprisingly dense population of galaxies compared to the surrounding universe, and they are filled with hot, diffuse gas, remnants of collapsed galaxies that emits faint X-rays, detectable by telescopes like Chandra and XMM Newton. But what makes them so scientifically valuable? The key is their isolation. Because supervoids are so extraordinarily empty, they provide an unparalleled opportunity to study dark matter without the confounding influence of visible matter. Most of the universe, approximately 85% of its total mass, is comprised of this elusive substance, a mysterious component that doesn't interact with light and therefore remains invisible to our telescopes. However, it does exert gravitational force. In galactic clusters, dark matter forms a vast halo surrounding the visible galaxies, providing the extra gravity needed to hold them together and shaping the distribution of galaxies within the cluster. Within supervoids, though, the concentration of this dark matter is dramatically reduced. Its effects are far easier to disentangle from that of ordinary matter. This allows scientists to isolate the signal of dark matter alone, almost like looking through a remarkably clear window into its behavior. Recent research has harnessed this unique feature to test and refine our models of dark matter interactions. The prevailing theory, known as cold dark matter, CDM, posits that dark matter particles were moving slowly in the early universe and clumped together gravitationally, forming the seeds for galaxy formation. But CDM hasn't always been entirely successful at predicting the observed distribution of galaxies and voids. One persistent puzzle was the missing satellites problem, where simulations predicted significantly more dwarf galaxies orbiting, larger galaxies than are actually observed. Supervoids provide a space to test the strength of dark matter interactions between these smaller satellite galaxies, and it has turned out that the simulations needed adjustments, essentially demanding weaker gravitational interaction between CDM particles to match what we see in the universe. scientists have been using supervoid observations to investigate the properties of dark matter itself, attempting to determine whether it interacts weakly with ordinary matter, or perhaps even interacts with itself through a process called self-interaction. These self-interactions would cause changes to the shape and structure of dark matter halos around galaxies. Researchers use computer simulations, incredibly complex calculations that attempt to recreate the conditions of the early universe, to model what happens when dark matter particles interact with each other. These simulations, often run on supercomputers, predict that self-interacting dark matter would create a slightly distorted, spiky appearance around galaxies rather than a smooth, spherical halo. By comparing these simulated distortions with observations of dark matter distribution in and around supervoids, using data from the Planck satellite to map the cosmic microwave background radiation, which provides clues about the early universe. Scientists are searching for this subtle signature, a way to experimentally test whether CDM is truly the correct model, or if modifications are needed. Current research involving voids extends far beyond simply confirming or denying darker matter models. It's pushing us closer to understanding fundamental physics itself. For example, the large-scale structure of the universe, the distribution of galaxies and voids, is deeply connected to the properties of gravity on scales much larger than those we typically study in laboratories here on Earth. The void environment allows for testing modified theories of gravity, alternative frameworks that attempt to describe how gravity works differently from Einstein's theory. Some theories propose that dark matter isn't simply a collisionless particle, but rather it interacts with itself or the fabric of spacetime in ways that would alter the way galaxies form and voids grow. The Sloan Digital Sky Survey, SDSS, has been instrumental in mapping supervoids and their surrounding galaxy populations at an unprecedented level of detail. This vast database provides a treasure trove of data for simulations and statistical analyses, allowing researchers to test models within well-defined regions of the cosmos. Researchers leverage these detailed maps, combined with sophisticated algorithms, to reconstruct the dark matter distribution within the voids, effectively creating a three-dimensional dark matter skeleton that reveals its subtle structure. Looking ahead, theoretical simulations are becoming increasingly sophisticated, incorporating more realistic representations of dark matter interactions and refining our understanding of galaxy formation processes. These simulations aren't just about reproducing observed data. They are about predicting the future evolution of the universe, how supervoids will continue to grow, how galaxies within them will evolve, and ultimately, how the large-scale structure of the cosmos will change over billions of years. One particularly intriguing line of research focuses on the possibility that supervoids themselves play a role in seeding the formation of new structures. Some scientists hypothesize that the gravitational pull of these vast empty spaces could initiate galaxy mergers within their boundaries, perhaps triggering bursts of star formation and leading to the creation of new galaxies, essentially acting as cosmic incubators. This is a largely speculative area of research, requiring further observation and detailed simulations, but it highlights the profound and far-reaching implications of studying these seemingly desolate regions of space. The study of supervoids isn't merely an academic exercise. It touches on some of the most fundamental questions about our universe. What is dark matter? How did the large-scale structure of the cosmos arise? And how will the universe evolve in the distant future? By peering into these cosmic shadows, we gain a deeper appreciation for the intricate and often counterintuitive nature of reality. It reminds us that even the most seemingly empty spaces can harbor profound secrets, offering a unique window into the workings of the universe's hidden forces. And as we continue to refine our observations and develop more sophisticated simulations, we're confident that supervoids will continue to yield invaluable insights, illuminating not just the distribution of galaxies, but the very processes shaping the fate of the universe itself, prompting even more profound questions about our place in its grand design. the insights, illuminating not just the distribution of galaxies, but the very processes shaping the fate of the universe itself, prompting even more profound questions about our place in its grand design. Now, let's turn our attention to a truly remarkable and unsettling feature of this vast cosmos: the supervoids, those colossal regions of seemingly empty space that stretch for hundreds of millions of light years, dwarfing entire galaxies in their scale. They are not simply dark patches. They represent an absence, a profound void within the otherwise structured fabric of reality. And as we begin to understand them, it becomes clear that their existence hints at possibilities far stranger and more energetic than many of us initially imagine. The question isn't merely where these voids are, but rather why they exist. What forces could sculpt such immense absences into the cosmic landscape? One compelling theory centers around a period of extraordinarily rapid expansion in the very early universe, a concept known as cosmological inflation. Cosmic inflation posits that, within fractions of a second after the Big Bang, the entire observable universe underwent an exponential burst of growth, expanding faster than the speed of light. It wasn't simply the universe growing larger, but rather the space itself was stretching at an incredible rate, carrying everything along with it. Imagine a balloon being inflated. Initially, the surface is smooth and unbroken. But as you pump air into it, the surface stretches, and any markings or patterns on that surface, like dots drawn on the rubber, become increasingly distant from each other. That's essentially what happened in those first fleeting moments after the Big Bang. The initial inflationary period was incredibly short-lived, lasting only a tiny fraction of a second, but its effects were profound, fundamentally shaping the large-scale structure we see today. The filaments and voids of galaxies arranged in a cosmic web. The models describing inflation aren't simply theoretical exercises. They are driven by mathematical solutions to Einstein's equations of general relativity, complex equations that attempt to describe gravity itself at the smallest scales. And those solutions predict, with surprising accuracy several key features of our universe, including the existence of these vast voids. Now, let's consider how these extreme density fluctuations, the seeds of the voids, might have arisen during inflation. During this period of hyperexpansion, tiny quantum fluctuations in the fabric of space-time, those minuscule uncertainties predicted by quantum mechanics, were stretched to enormous scales. Think again of the balloon analogy. Those dots on the rubber aren't just randomly placed anymore. They are now separated by huge distances because the surface is expanding so rapidly. The regions that experienced slightly more expansion during inflation became progressively less dense. These are the areas destined to become supervoids. Conversely, the regions that underwent slightly less expansion became denser, eventually collapsing under their own gravity to form clusters of galaxies and other structures. It's a remarkably elegant picture. An initial quantum uncertainty magnified by the extreme conditions of early inflation, resulting in the large-scale architecture of the cosmos. And crucially, this process doesn't require any pre-existing structure. It creates the structure. The voids, as well as the galaxies, from an almost entirely uniform state. The simulations used to explore these inflationary models are truly breathtaking. Visualizations that attempt to capture the fleeting moments of creation. You'll often see renderings depicting a rapidly expanding space, punctuated by swirling patterns and iridescent color gradients. These aren't literal representations of what happened necessarily. They aim to convey the feeling, the immense scale, the exponential change of this period. Researchers use sophisticated computer power to model the behavior of fields during inflation, tracking how these quantum fluctuations grow and evolve as the universe expands. The results often show regions where density contrasts become starkly pronounced, highlighting the formation of potential void sites. One particularly compelling representation frequently involves a three-dimensional foam, a complex lattice structure interwoven with bright, expanding bubbles representing areas of growth and compression. It's a visual metaphor for the chaotic, yet ultimately ordered process that that shaped our universe in its infancy. These models aren't perfect, of course, as they are still extrapolating from limited observational data, but they provide increasingly detailed insights into the mechanisms driving cosmic inflation. The key to understanding these voids lies in grasping the role of the inflaton field itself. This is a hypothetical energy field that's theorized to have driven the inflationary epoch. Scientists don't yet know what this field actually is, or how it interacts with matter and energy, but its existence is mathematically necessary to explain inflation. As the inflaton field rapidly expanded, it created an enormous amount of potential energy, which then converted into the observable universe through a process called reheating. This reheating event essentially smoothed out many of the initial quantum fluctuations, leaving behind the relatively uniform distribution from which galaxies and voids subsequently formed. The size of the supervoids we observe today depends critically on the precise parameters governing inflation. Things like the duration of the inflationary period, its rate of expansion, and ultimately, the strength of gravity itself. The scale of these voids is profoundly puzzling because our current models struggle to fully explain their immense proportions without invoking some form of exotic physics or fine-tuning. Simply extrapolating from the standard cosmological model, which incorporates dark matter, dark energy, and ordinary matter, doesn't quite account for the observed void sizes. Some researchers have explored scenarios involving multiple inflationary epochs, rapid bursts of expansion separated by periods of cooling, as a possible explanation. Others suggest that gravity itself might be slightly different in the voids than it is in the surrounding universe. It's a subtle possibility, but one that could significantly impact the evolution of these colossal spaces. Current observations of the cosmic microwave background, the afterglow of the Big Bang, provide some constraints on inflationary models and can help us refine our understanding of how these early conditions shaped the cosmos. The distribution of galaxies within supervoids presents another intriguing puzzle. While it's expected that voids would lack galaxies, an absence of matter what we actually observe is something more complex. Instead, many supervoids contain a surprising number of satellite galaxies, orbiting dwarf elliptical galaxies at their centers. It's as if the regions are gravitationally attracting and retaining these smaller structures against the pull of surrounding filaments. This suggests that there may be some subtle interaction between matter and the void itself, perhaps involving dark matter that's influencing the dynamics of these satellite galaxies. Investigations using data from telescopes such as Hubble continue to reveal more details about this population, offering clues towards a deeper understanding. Furthermore, the study of supervoids isn't just an academic exercise in cosmology. It has implications for our broader understanding of dark energy and the accelerating expansion of the universe. The voids themselves are regions where gravity is weaker than average, which could influence the rate at which space expands. Precisely quantifying this effect remains a significant challenge, but it highlights the interconnected nature of these cosmic features. The exploration of supervoids, therefore, represents more than just an investigation into the architecture of the early universe. It's an attempt to unravel the deepest mysteries about the forces that govern its evolution, and ultimately, what might lie beyond our current observational horizon. As we probe these dark corners of the cosmos, asking not just what they are, but how they arose, and what their implications are for the future of everything. We're inevitably drawn closer to the very origins of space and time itself. And that, in its essence, is the profound beauty and perhaps the daunting challenge of studying these enigmatic supervoids. Thinking about it again, with the vast scale involved, one can begin to imagine a truly alien experience for any potential traveler venturing into such a region. The relative lack of light would be absolute, a permanent twilight punctuated only by the faint glimmer of distant galaxies, if they could even see them at all. The temperature would plummet to near absolute zero, an environment where even the most advanced technology would struggle to function, and the gravitational forces, though weaker than in galaxy clusters, would still exert a noticeable influence. subtly altering movement and perhaps even affecting perception. It's a scenario that stretches the boundaries of our imagination, forcing us to confront the limits of human experience and wonder at the sheer strangeness of the universe. It's a reminder that we are inhabitants of just one small corner of an unimaginably vast and complex cosmos, and that these enormous voids represent perhaps the starkest evidence yet of how little we truly understand about our surroundings. Let us consider now the subtle yet pervasive influence of dark energy, a force that remains something of a profound enigma, even as we gain increasingly detailed insights into its behavior. For decades, cosmologists observed an accelerating expansion of the universe, a phenomenon initially perplexing because gravity, from Newtonian physics to Einstein's own theory of general relativity, predicts a slowing down of such vast scales. The prevailing assumption was that all matter and energy in existence exerted a gravitational pull, attempting to draw everything together, a relentless inward tug counteracting the outward push of the expanding space itself. But the observations were clear. Galaxies weren't just receding, they were speeding away from each other at an increasing rate. This led to the revolutionary concept of dark energy, something filling space not through attraction, but pushing it outwards, creating a negative pressure that overwhelms gravity on cosmic scales. We don't understand its source, whether it's a property inherent in the vacuum of space itself, or perhaps connected to quantum fluctuations at the very beginning of time. But we know it's there, making up roughly 68% of the total energy content of our universe, and driving this relentless expansion. You can think of it like this. Imagine stretching a rubber sheet. You apply pressure in the center, and it curves inward. Now, if instead someone began to blow air into the sheet from all directions at once, a uniform outward flow, the sheet would expand rapidly without any central point of compression. Dark energy behaves somewhat similarly, although on an unimaginably grand scale. It's not a force pulling down, but rather it's acting as a constant pressure, pushing space outwards. smoothing out the wrinkles and rifts within the fabric of space-time itself. The effects are so subtle over earthly timescales that we wouldn't notice them directly. A star born today will still be drawn in by gravity. A planet orbiting a sun will continue its journey around it, but across billions of years. This constant expansion becomes undeniably apparent, and this accelerated expansion is the very engine that fuels the formation and evolution of cosmic structures, including those enormous voids we've been discussing. Now let's turn our attention to these supervoids, immense, nearly empty regions of space that appear to be actively growing, defying all expectations of gravitational collapse. They are like colossal vacuum cleaners, sucking in galaxies and dimming the light from distant quasars. They're almost impossible to reconcile with our current understanding of how gravity should operate on such scales. The standard cosmological model predicts that after the initial period of accelerated expansion initiated by dark energy, matter should gradually clump together due to gravitational attraction, eventually leading to a more balanced distribution of galaxies and a slower rate of expansion. However, observations reveal the opposite. These voids are expanding at an alarming rate and appear to be getting larger over time, a phenomenon that has challenged theoretical physicists for years. Perhaps one of the most intriguing questions surrounding supervoids is whether dark energy might be playing a more direct role in their formation and growth than previously assumed. Early models suggested that the expansion itself, driven by dark energy, might create regions where the density of matter is naturally lower, effectively pre-structuring space and allowing voids to form and expand more readily. It's akin to ripples on a pond. An initial disturbance can propagate outward, leaving behind areas with less water. In this analogy, less matter. The underlying theory proposes that dark energy creates regions of slightly reduced density during the early universe, a subtle imbalance that then amplifies through subsequent expansion, leading to the formation of these colossal voids in time. It's not a simple cause and effect relationship. Rather, It's a complex interplay between the accelerating expansion and the distribution of matter seeded by earlier gravitational fluctuations. To explore this possibility further, cosmologists rely heavily on cosmological simulations, incredibly powerful computer models that attempt to recreate the evolution of the universe from its earliest moments to the present day. These simulations incorporate our best understanding of dark energy, dark matter, ordinary matter, and the laws of gravity, but they are still subject to many uncertainties and approximations. You'll see here, in this simulation, the visuals will slowly rotate, revealing a 3D representation of cosmic space. A snapshot from one such model, illustrating the distribution of galaxies across billions of years. Notice how the initial fluctuations created by inflation, tiny quantum variations in the density of the early universe, grow into larger structures over time. Galaxies, clusters of galaxies, and even large-scale voids. As you watch this simulation progress forward in time, observe how these voids appear to grow at an accelerated rate, expanding outwards as a consequence of dark energy's relentless push. The color variations represent the density of matter. Darker shades indicate regions with higher concentrations of galaxies, while lighter hues signify vast expanses of empty space. A clear visual representation of the void structure. Within these simulations, researchers tweak various parameters, the strength of dark energy, the initial conditions of the universe, the nature of gravity itself, to see how these changes affect the evolution of cosmic structures. By comparing the results of different simulations with observational data from telescopes like Hubble and JWST, scientists are trying to refine our understanding of the fundamental forces that govern the universe. Now consider this further example. The simulation shifts focus. A more detailed view focusing on a single region where two supervoids are interacting. The visual effects show how the edges of these voids aren't simply expanding outwards. They're actually absorbing surrounding galaxies, drawing them into their emptiness. This is particularly striking in regions near the collision of two potentially merging voids. The simulation demonstrates that this process isn't solely driven by the overall expansion of dark energy, but also by subtle variations in its distribution, perhaps related to topological defects in spacetime itself, something increasingly theorized. It's as if the voids are actively hunting for matter, relentlessly consuming everything within their gravitational reach. The relative growth rates of these supervoids are a crucial area of research. Some simulations indicate that certain voids are growing faster than others, suggesting a hierarchical structure. Larger voids containing smaller ones, and so on. This raises the question: is there some intrinsic property of dark energy that favors the formation of particular void configurations? Or is the growth rate simply a consequence of the initial conditions of the universe and the chaotic nature of gravitational collapse? These are questions that remain open for debate, and one of the main drivers behind ongoing cosmological research. Furthermore, it's possible that dark energy itself isn't entirely uniform across the universe, that its strength varies spatially or temporally, a concept known as dynamic dark energy. If true, this could explain why some voids are growing faster than others. Regions with higher concentrations of dark energy would simply provide a stronger gravitational pull, accelerating the growth rate within those zones. Detecting such variations in dark energy's density is an enormous challenge, requiring extremely precise measurements of the cosmic microwave background radiation and other cosmological probes. Ultimately, understanding the role of dark energy in shaping supervoids, and indeed in driving the expansion of the entire universe, represents one of the most significant scientific challenges of our time. It requires a fundamentally new approach to cosmology, moving beyond simply describing what is and towards unraveling the why, the underlying mechanisms that govern the evolution of the cosmos. These enormous voids aren't just empty spaces. They are potentially fingerprints left behind by the enigmatic force that is reshaping our understanding of reality, reminding us that we are still perched at the edge of comprehending the grandest scales imaginable, and that these dark corners hold secrets far exceeding our current grasp. The universe continues to reveal its mysteries, inviting us onward into realms where our intuitions struggle and our theories must constantly adapt. The concept of a supervoid, a region of space so vast that galaxies simply don't form within it, emerged from observations of the cosmic microwave background, the faint afterglow of the Big Bang. It was a startling discovery, suggesting that large-scale voids exist across the universe, seemingly defying our expectations of how matter should distribute itself. We initially imagined these to be solitary entities, vast, empty islands in an otherwise populated ocean of galaxies. But as we've refined our surveys and deepened our understanding of cosmological structure, a more complex picture has begun to emerge, one that suggests these colossal voids aren't alone. They appear to be gathering together, forming clusters, collections of adjacent supervoids that dramatically reshape our view of the cosmos. Let us consider, then, what it means for the universe when these immense absences begin to congregate. The prevailing cosmological model, based on dark matter and dark energy, posits that structures in the universe, galaxies, clusters of galaxies, and filaments, grew from tiny fluctuations in density during the early universe. These overdense regions attracted more matter through gravity, eventually collapsing to form the large-scale patterns we observe today. However, if supervoids are truly a consequence of this growth process, then it stands to reason that they too should participate in the aggregation. They wouldn't simply be static entities. They'd be subject to the same gravitational forces as everything else, a concept initially unsettling for many cosmologists. The question isn't just where these voids are located, but how they end up grouped together. One leading hypothesis centers around the void invasion model. This suggests that supervoids aren't simply born in isolation. Instead, they represent regions where the underlying dark matter distribution has been profoundly disrupted. Imagine a ripple across a still pond, a disturbance of matter. In this analogy, supervoids could be interpreted as zones where dark matter hasn't had sufficient time to clump together and form the gravitational wells that attract galaxies. As such, these areas become incredibly underdense. Now, if you imagine an expansion within that void, an outward push from the surrounding density, you begin to understand how a void might invade adjacent regions. It's not a violent collision, but more like a slow, creeping absorption of matter, gradually diminishing the density of neighboring structures until a supervoid is established. The relative speed and scale of this invasion would be determined by the expansion rate of the universe itself, a constant factor in the unfolding drama of cosmic evolution. The deeper you go into cosmological simulations, the more credence we give to this model as an explanatory force. Furthermore, it's possible that these void clusters aren't forming simply through a single invasion event, but through repeated cycles of formation and growth. A supervoid might initially form in one area, then slowly expand outwards, drawing matter from its surroundings. As it grows larger, it may attract another nearby void, initiating a new phase of invasion. These processes could repeat themselves over billions of years, resulting in complex, hierarchical structures, giant voids nested within smaller voids, and these smaller voids again connected to even larger void clusters. It's like a cosmic game of dominoes, where each falling piece triggers the next. Visualizing this isn't easy, but we can use computer simulations to illustrate how such arrangements might arise. Consider an image generated from data collected by the Planck satellite, showing the distribution of matter in the universe at a particular epoch. The brighter regions represent areas with higher density where galaxies are found. The darker regions indicate the voids. Now imagine applying a subtle animation that simulates the void invasion process. You'll see faint tendrils of darkness gradually spreading outwards from existing supervoids, slowly filling in the surrounding space. These aren't sharp boundaries. The transition is gradual, suggesting an ongoing evolutionary process. Another way to represent these clusters is with a three-dimensional map, where the color intensity corresponds to the density of matter. You might see large, empty pockets surrounded by a faint halo of slightly lower density. It's not as dramatic as a nebula or galaxy cluster, but it speaks to this fundamental void structure. These visualizations are based on sophisticated models that incorporate dark matter simulations and observational data from surveys like the Sloan Digital Sky Survey. The results consistently suggest that void clusters are more common than initially anticipated, perhaps accounting for a significant fraction of the total volume of the observable universe. They are there, hidden in the deepest shadows, influencing the distribution of galaxies without necessarily being directly visible. It's important to note that these dark regions aren't completely devoid of matter. There are galaxies within supervoids, though they are far sparser than those found in galaxy clusters. These isolated galaxies have adapted to survive in extraordinarily low-density environments, often exhibiting unusual properties and morphologies. Some are extremely faint and diffuse, while others display peculiar shapes or colors due to their unique surroundings. Studying these void galaxies provides valuable insights into the dynamics of star formation and galactic evolution under extreme conditions. They are like resilient survivors, clinging to existence in a place where most other life would simply fade away. The discovery of void clusters has profound implications for our understanding of dark matter. The current standard model of cosmology assumes that dark matter follows a smooth distribution on large scales, determined primarily by the initial density fluctuations in the early universe. However, if supervoids are forming through an invasion process driven by variations in dark matter density, then this assumption needs to be reconsidered. Perhaps we're missing a key ingredient, a mechanism that influences how dark matter collapses and forms voids. Exploring alternative models of dark matter, such as self-interacting dark matter or modified Newtonian dynamics, MIND, could potentially provide an explanation for the observed void clusters. Furthermore, these clusters challenge our notions about the overall geometry of the universe. The distribution of supervoids, their size, shape, and connectivity could reveal subtle clues about whether the universe is flat, curved, or something in between. Measurements of the cosmic microwave background provide strong evidence for a nearly flat universe. But anomalies in the large-scale structure might suggest that there are deviations from this expectation. The location and arrangement of void clusters could serve as another data point to constrain cosmological parameters and test our theories about the evolution of the universe. As we continue to refine our observational capabilities with newer telescopes and more sophisticated survey techniques, we can expect to uncover even more surprising details about these dark behemoths and their clustering patterns. The James Webb Space Telescope, for example, is already providing unprecedented views of distant galaxies and voids, allowing us to study the formation and evolution of galaxies within these extreme environments. Future surveys will map the distribution of matter with increasingly greater precision, revealing a far richer tapestry of cosmic structures than we currently understand. The existence of void clusters isn't just an interesting quirk of cosmology. It's a fundamental puzzle that forces us to reevaluate our understanding of how the universe works. It's a reminder that the cosmos is not simply a smooth, predictable entity, but rather a complex and often counterintuitive place filled with surprises waiting to be discovered. It's humbling, in fact, to realize that what we believe to be fundamental truths are constantly being questioned by new observations and theoretical insights. These voids remind us that our models of the universe, elegant as they may appear, are ultimately approximations, attempts to capture a reality that is infinitely more vast and mysterious than we can ever fully comprehend. They force us to embrace uncertainty, to acknowledge the limits of our knowledge, and to continue exploring, driven by a simple yet profound curiosity about the nature of existence itself. The secrets hidden within these immense absences hold challenges for science and inspire awe in equal measure. Now let us turn our gaze outwards again, further than ever before. Considering the perspective of instruments traveling at near constant speed through a vast expanse, specifically the Voyager probes. These small spacecraft, launched decades ago with an initial mission to study Jupiter and Saturn, have continued their journey, propelled by the relentless inertia of space itself, carrying with them a silent testament to our enduring curiosity. It's remarkable, really, that they are still transmitting data after all this time, a steady stream of information from an increasingly distant corner of existence. But it's not just the data we should focus on, but how they've traveled and what that tells us about the cosmos itself. Voyager 1 and Voyager 2, now beyond the heliopause, where our solar system's influence fades into the interstellar medium, are carrying us along with them, offering a unique, albeit profoundly constrained, vantage point on the universe as a whole. They are not explorers in the traditional sense, of course. They lack eyes, and yet they have become, in a way, cosmic cartographers, charting a route through the void that reveals the shocking emptiness, the supervoids, that dominate much of our observable universe, alongside the brilliant clusters of galaxies we readily see. Their trajectories aren't random. They are meticulously calculated to maximize data collection and maintain communication with Earth. But those calculations, driven by the demands of their original missions, and now solely based on solar radiation pressure and small course corrections, have inadvertently provided us with a remarkably precise understanding of the relative distances between these colossal voids. Think about it. Voyager is moving at approximately 17 kilometers per second. Over the decades, that speed has allowed it to traverse countless millions of kilometers, tracing an ever-expanding arc through interstellar space. Each telemetry packet received from those probes represents a tiny piece of a grand cosmic map, painstakingly constructed by their relentless journey. As we analyze the data streams, the faint signals bouncing off distant spacecraft, the subtle variations in solar flares, we can overlay these trajectories against maps of the intergalactic medium and begin to grasp with increasing clarity the sheer scale of the vast stretches of space that lie between the galaxies, The distances aren't simply large, they are staggeringly immense, often stretching for hundreds of millions, even billions of light years. Voyager's passage isn't a direct line through the universe. Of course, it moves with a slight curve, influenced by the gravitational pull of our Sun and other stars in the Milky Way. But this curvature is precisely what allows us to interpret its motion as a kind of cosmological yardstick. The probes aren't actively measuring these voids per se, but their consistent movement through them. The sheer time it takes for signals to reach Earth from increasingly distant points provides irrefutable evidence of their existence and the breathtaking gulfs that separate them. It's a subtle, almost ethereal kind of measurement, relying on the fundamental physics of radio waves and the unwavering speed of those tiny spacecraft. But its implications are profound. The Voyager probes represent one of our most elegant demonstrations of the scale of the cosmos, a silent testament to the fact that we can learn astonishing things about the universe simply by observing how things move through it. Now, let's be clear. Studying these structures with robotic probes is an inherently limited endeavor. These are not instruments designed for large-scale surveys. They were built for specific tasks: mapping planetary surfaces, characterizing planetary atmospheres, and relaying data back to Earth. The primary goal wasn't to map the intergalactic void, but it turns out that they were surprisingly adept at doing just that. Simply by continuing their mission, the challenges are significant. Voyager's instruments are relatively simple compared to modern telescopes. They lack the resolution needed to directly image the voids themselves. Instead, they detect subtle changes in the cosmic background radiation, the faint afterglow of the Big Bang, as it passes through these regions of space. Any temperature fluctuations, minuscule shifts in the intensity of this background glow, can be attributed to interactions with dark matter, or perhaps even the gravity of unseen structures within these voids. But interpreting those fluctuations requires sophisticated modeling and a deep understanding of cosmology, a process that's still unfolding as we gather more data. Furthermore, Voyager's perspective is restricted by its trajectory. It moves in one direction through space, constantly away from us. It can only look back at the regions it has traversed, providing a moving map of the universe as seen from an ever-increasing distance. It's like tracing a river with a single drop of water. You get a sense of the overall flow, but you miss much of the complexity that exists along its banks. To truly appreciate the scale and nature of these voids, and to simulate Voyager's perspective, we can employ computational techniques to generate visualizations. These aren't literal renderings of what the probes are seeing, of course. Rather, they are artistic interpretations based on the data gathered and our understanding of cosmology, using models of the cosmic microwave background, combined with simulations of Voyager's trajectory and its interaction with the intergalactic medium. We can create images that attempt to convey what it might feel like to be traversing these regions of space. One such simulation shows Voyager, rendered as a small, simple probe, slowly moving across a vast, dark expanse. The background is filled with an incredibly diffuse glow, representing the cosmic microwave background. But interspersed throughout this glow are enormous swaths of almost complete darkness. These dark patches represent the supervoids, regions where the density of galaxies is far lower than average, where the distribution of matter is unnaturally sparse. The simulation emphasizes the staggering distances between these voids. Voyager appears incredibly isolated, surrounded by an endless sea of emptiness. Another visualization focuses on the arrival of a faint signal from Voyager. As it traverses one of these voids, the image shows the probe streaking across a starfield, seemingly alone in a vast and silent universe. The colors are muted, deep blues and purples, reflecting the coldness and darkness of interstellar space. There's no sense of excitement or discovery here, just a quiet, methodical journey through an improbable void. These simulations aren't meant to be dramatic or sensationalized. They are intended to provide a tangible sense of the scale and isolation that characterize these regions of space, to embody the very essence of their existence as the scariest places in the universe. the probes continue their journey, silently accumulating data. As we receive each signal, a little more of the cosmic map is revealed, a little more precision with which we can measure the distances between galaxies and the scale of these colossal voids. It's a testament to human ingenuity and perseverance, to our unwavering desire to understand the nature of existence, even from such a distant vantage point. And as Voyager drifts further into the interstellar sea, carrying its silent message across billions of kilometers, it serves as a poignant reminder that our exploration of the universe is not just about discovering new planets or visiting distant stars. It's also about appreciating the profound and humbling reality of our place within this vast and largely empty cosmos. The data they transmit speaks more than words could ever convey. A slow, steady confirmation of how much is unseen, how profoundly different the universe truly is from our familiar view. It's a perspective that invites quiet contemplation, a recognition of the unimaginable distances and unsettling silences that define the boundaries of our observable world. The patterns we've glimpsed so far, the faint echoes of galaxies lost in this cosmic ocean, they are like tentative brushstrokes across a vast, unfinished canvas. A feeling remains, perhaps, that the deeper we look, the more profoundly bewildered we become. And bewilderment shouldn't be mistaken for failure. Rather, it should be welcomed as a signal of truly unexplored territory. The universe often presents itself not as something to conquer or understand entirely, but as a puzzle whose most compelling beauty lies in its persistent mysteries and the relentless effort required to nudge closer toward their edges. Now, let us consider what future observations might reveal about these immense empty spaces, these supervoids that seem, paradoxically, to be the heart of the cosmic network. The immediate horizon of supervoid research is remarkably bright, fueled by a confluence of ambitious new space telescopes and evolving observational strategies. The Roman Space Telescope, currently in development at NASA, represents a significant leap forward. It's designed with an unprecedented suite of cameras. Nancy Grace, Lucia, and Marco Polo, specifically tailored to study faint, diffuse light from the early universe. Crucially, these instruments are sensitive not just to visible and infrared light, but also to Lyman alpha emission, a process where hydrogen atoms emit ultraviolet light when they absorb energy. This ability is profoundly important because supervoids, being regions of exceptionally low density, would have experienced a far greater abundance of neutral hydrogen in the early universe than denser regions. Therefore, observing this emitted light will allow Roman to create some of the most detailed maps ever produced of the distribution of gas, and therefore galaxies within and around these voids. We are beginning to imagine seeing a ghostly shimmer tracing the boundaries of these colossal absences, a map that will extend our understanding of how the early universe's matter assembled itself into the structures we observe today, beyond simply mapping their extent and density. Researchers are developing innovative techniques for unraveling the complex dynamics involved in supervoid formation and evolution. One promising avenue involves gravitational lensing, a phenomenon where the gravity of a massive object, like a galaxy cluster, bends and distorts the light from objects located behind it. Supervoids themselves can act as gravitational lenses, magnifying and distorting the light from distant galaxies on the other side. By analyzing these distorted images, what scientists call lensed arcs, we can not only learn more about what lies within the void itself, but also gain insights into the overall distribution of dark matter, the invisible substance that makes up a significant portion of the universe's mass and dominates its gravitational effects. Dark matter, in essence, is structuring these voids, creating subtle distortions in space-time that are detectable through this lensing effect. Furthermore, future surveys utilizing adaptive optics, technology that corrects for atmospheric turbulence, will provide sharper images than ever before, enhancing the accuracy with which we can measure these distortions and map out the underlying distribution of dark matter in greater detail. The James Webb Space Telescope's continued observations will also play a critical role. While initially designed to study distant galaxies, JWST's infrared capabilities open new possibilities for studying the properties of the gas within supervoids, particularly its temperature and composition. By analyzing the infrared light emitted by hydrogen atoms in these voids, scientists can probe the extreme conditions present, temperatures that are unexpectedly cold, even considering cosmological distances. These unexpectedly low temperatures have led to a great deal of speculation about the mechanisms driving this cooling, and researchers are exploring various possibilities, including feedback processes from supernova within the sparse galaxies that might inhabit the voids, or perhaps even more exotic explanations involving interactions with the cosmic microwave background radiation. But let's consider something beyond simply refining our current understanding. What if the supervoids themselves hold surprises? The prevailing theory posits that they are remnants of a period in the early universe when matter was distributed much more uniformly, a time before the gravitational forces had fully coalesced into the familiar cosmic web of filaments and voids. However, recent simulations suggest that there might be several distinct types of supervoids, each with its own unique formation mechanism and evolutionary pathway. For instance, some researchers propose that certain supervoids could represent regions where early density fluctuations were simply amplified, where pockets of slightly higher density in the pristine early universe grew to colossal proportions through gravitational instability. This would differentiate them from other void types that are thought to have formed due to the merging of smaller voids over billions of years. Another intriguing possibility is the existence of void bubbles, regions completely devoid of galaxies and dark matter, essentially pockets of space that were never significantly influenced by the early gravitational collapse. These bubbles might have arisen during a period of particularly violent cosmic expansion, a big bounce scenario, where the universe underwent a rapid contraction followed by an equally abrupt expansion. The prospect is difficult to imagine, but mathematically plausible given our current understanding of cosmological evolution. Imagine encountering such a space, not just as emptiness, but as a distinct entity within the grand framework of reality, a profound separation that challenges our notions of continuity and connectedness. Then there's the speculative idea of dark void clusters, collections of supervoids gravitationally bound together. The current view is that they are largely isolated structures. But if these larger groupings exist, they could dramatically alter our understanding of void dynamics. They would imply a more complex network of gravitational interactions within the universe, a system where the distribution of matter isn't simply governed by individual voids, but by the collective influence of multiple interconnected spaces. Detecting such clusters will require extremely precise measurements of the positions and motions of galaxies across vast distances, pushing the capabilities of future astronomical surveys to their limits. Furthermore, scientists are investigating whether supervoids could be linked to large-scale structures known as cosmic filaments. These filaments represent the largest structures in the universe, giant strands of dark matter and gas that connect galaxies into a cosmic web. Some theories propose that supervoids might have formed within these filaments, essentially creating holes in the network of interconnected structures. This would suggest a hierarchical relationship between voids and filaments, a complex interplay of assembly and disassembly as the universe evolved. It's also worth considering the possibility of entirely new types of void, voids that don't fit neatly into any existing category. Perhaps there are configurations where supervoids merge with galaxies, creating hybrid structures that challenge our current models of galaxy formation. Or perhaps we will discover regions where the laws of physics themselves behave differently, where the distribution of dark matter is significantly altered, or where the expansion rate of space deviates from the standard cosmological model. The sheer scale and complexity of the universe mean that we are almost certainly on the cusp of uncovering phenomena we haven't even dreamt of yet. Ultimately, research into supervoids isn't just about mapping empty spaces. It's about illuminating the fundamental processes that shaped the universe as we know it. These colossal voids are not merely absences. They are active participants in the cosmic drama, influencing the distribution of galaxies and providing a unique laboratory for testing our theories about gravity, dark matter, and the evolution of structure. As we continue to build more powerful telescopes and develop increasingly sophisticated observational techniques, we are certain to gain an ever deeper appreciation for the profound mysteries hidden within these darkest secrets of the cosmos, and perhaps in the process refine our grasp of what it truly means to exist within this grand, silent, and utterly astonishing universe. And perhaps in the process refine our grasp of what it truly means to exist within this grand, silent, and utterly astonishing universe. Now, as we turn our gaze inward, away from the breathtaking distances previously explored, something shifts subtly. The scale we've been navigating, light years compressed into minutes of observation, galaxies collapsing into digestible segments, begins to yield, gently retreating, a slow, deliberate unwinding. The intricate dance of celestial bodies softens, and a familiar perspective returns, one that anchors us firmly to the reality of our own planet. Before us, the Earth unfolds, not as a vibrant sphere teeming with life, but as a serene blue marble suspended within an endless ocean of black. It's a view both profoundly intimate and breathtakingly distant, suddenly rendered small by the sheer magnitude of everything we've just witnessed. You see it now, this perspective that you are here, on this tiny spinning world, caught in the quiet gravity of a single star, orbiting a sun utterly unremarkable in the grand cosmic scheme, but undeniably vital to your existence. The feeling is not one of diminished importance, though rather an amplified sense of connection. It's a recognition that our scale isn't defined by the distances we can travel amongst the stars, but by the delicate web of circumstances that allows for life to blossom on this single point of light. Consider the vastness of space, truly vast. We spoke earlier of supervoids, these colossal regions where galaxies simply aren't. where the concentration of matter is so incredibly low that light itself struggles to escape their gravitational clutches. They represent absences, voids in the fabric of space-time, and their existence is still a subject of intense scientific debate, largely because their sheer size defies our current understanding of how large-scale structure forms. But as we return to Earth, surrounded by the familiar blue hues of its atmosphere and oceans, it's essential to acknowledge just how profoundly unusual this planet truly is. Its location within this grand void, a relatively unremarkable corner of the observable universe, underscores the improbable nature of our existence. The odds of Earth existing in one of these immense expanses are astronomically low, bordering on incomprehensible. We can trace the origins of this void to the early universe, believed to have been dominated by a process called cosmic inflation, an exponential expansion from an infinitesimally small point that happened fractions of a second after the Big Bang. This rapid stretching created enormous fluctuations in density, leading to pockets of higher and lower concentration. These pockets then served as seeds for the formation of galaxies and galaxy clusters, eventually coalescing into the large-scale structures we observe today. But some regions remained vastly underdense. These are the supervoids. Scientists suspect that a combination of factors contributed to their creation. Perhaps subtle variations in the density of the primordial plasma, or potentially even larger fluctuations within the inflation itself. The leading ideas involve analyzing patterns of cosmic microwave background radiation, the afterglow of the Big Bang, looking for subtle distortions that might hint at these initial fluctuations. It's a challenging puzzle, and one that continues to occupy many astronomers as they strive to understand the fundamental processes shaping our universe. And yet, here we are, safe within this local patch of existence. The very light that illuminates your screen tonight has traveled for countless millennia, spanning billions of years to reach you, carrying with it echoes of distant galaxies, reflections of supernova long extinguished, and perhaps even glimpses of the supervoids themselves. It's a humbling thought, isn't it? That the smallest flicker of illumination in our lives is connected to events that occurred long before our ancestors walked upon this planet and will continue to resonate far beyond our own time. You might feel a current, a subtle pull towards something larger than yourself, a recognition of belonging within an unfolding narrative spanning cosmic timescales. The sheer emptiness, the profound silence of these supervoids is not simply a lack of matter. It's a fundamental absence of gravitational influence. They represent regions where the fabric of space-time itself seems to thin, where the usual rules of physics operate in subtly altered ways. Think about how gravity shapes our reality here on Earth. It dictates the orbits of planets, the fall of raindrops, and the very structure of mountains. But within a supervoid, this familiar force is dramatically weakened, leading to unusual effects that scientists are only beginning to understand. For instance, light itself bends more readily in these regions, creating distorted images of distant galaxies, a phenomenon known as gravitational lensing. It's like looking through a warped lens, revealing hidden details and stretching the boundaries of our perception. Consider, too, the implications for the formation of structures within the universe. Galaxies tend to cluster together, drawn by mutual gravity. But supervoids disrupt this process, creating enormous gaps in the cosmic web. Vast regions devoid of galaxies. These voids are not necessarily empty. They contain diffuse gas and dark matter, which interact with the surrounding environment through subtle gravitational forces. The distribution of these components is complex and still poorly understood. However, observations from telescopes like Hubble have revealed that supervoids exist on a truly staggering scale, some spanning hundreds of millions of light years across. They are not simply local anomalies. They represent fundamental features of the large-scale structure of the universe. Returning to this earthly perspective, it's hard to shake off the sense that we've glimpsed something both terrifying and exquisitely beautiful about the cosmos. These supervoids, these immense dark spaces, are a stark reminder of our own insignificance. Yet simultaneously, they reveal the remarkable resilience of the universe to create order out of chaos, to form galaxies and stars, even in the most unlikely places. The universe doesn't seem concerned with our comfort or convenience. It simply is. It's an expansive indifference that can be profoundly unsettling, but also strangely liberating. As you settle into stillness now, allow yourself to appreciate the quietude of this moment, the gentle rhythm of your breath, the warmth against your skin, the subtle sounds of the world around you. These are gifts. They represent a temporary reprieve from the vastness and mystery of the cosmos. Don't seek answers in the grandeur of distant galaxies or the complexities of dark matter. Instead, find peace within the simplicity of this present moment. Consider the feeling of grounding yourself, that feeling of being rooted in your body, connected to the earth beneath you, breathing deeply into a space filled with possibility and potential. Let go of any lingering thoughts about the infinite distances we've traveled, the unimaginable scales involved in these cosmic phenomena. Turn inward towards this quiet center within yourself. It is a place of stillness, of reflection, of simply being. The universe unfolds around you, relentlessly expanding and evolving. Yet here, in this single point of awareness, there is only calm. There is only peace. And as the light begins to fade, allowing the shadows to lengthen, remember that even within the darkest corners of space, within these immense supervoids, there's a quiet beauty, a stillness that mirrors the stillness you now hold within yourself. May this awareness, this recognition of our place in a universe, both magnificent and profoundly silent, bring you rest and serenity. Let your thoughts drift effortlessly, like clouds across a boundless sky. Close your eyes if it feels right, and simply breathe, knowing that even amidst the greatest mysteries, there is always a space for quietude. The immense emptiness stretches onward, a silent testament to the vastness we barely comprehend. These supervoids, regions of space so profoundly empty that galaxies simply refuse to form within them, pose questions about the very fabric of space-time, about how such colossal voids could exist and what they might reveal about our own place in the universe. It's humbling to consider these dark realms, a reminder of the limits of our perception, and an invitation to continue seeking answers among the stars. Let your thoughts drift amongst them now and find solace in this quiet, distant beauty. Thank you for spending this time among the stars with me. If you enjoyed the journey, a gentle like and a subscribe help more quiet dreamers find their way here. Until next time, rest well and keep wondering about the cosmos. Good night.